So far, if I would like to take a big panoramic survey of the course, we've completed one module. The first module that we've completed deals with the strangeness of quantum physics, the counterintuitive, non-commonsensical, highly baffling results from quantum physics, entanglement, superposition, interaction-free measurement, the quantum Zeno effect. You keep on looking at something, it does not evolve, quantum algorithms, the power of quantum parallelism, doing many things at once with the help of superposition, the properties of quantum teleportation, and so on. So the first module of this course was really focused on the strangeness of quantum physics. Today we're going to start this second section of this course, and in this course I'm going to talk more about physical systems. So this is the physicality of quantum physics that I'm going to really talk about starting today. Now when I start talking about physical quantum systems, an important aspect is to see how do systems change with time. You've already taken a course on mechanics. What was that course all about? If you would like to give me a summary of that course in one or two sentences. So what was mechanics all about? Modeling physical situations, but you didn't touch quantum physical systems. So what does mechanics mean? Yes?
The evolution of a system given the initial conditions.
Right. So what does evolution mean? You're not talking about biological evolution here, I'm of course.
How it evolves over time.
How something changes with time. So how something changes with time is really important. That's called kinematics. And there is also this subject called dynamics, in which you look at the forces acting on an object. So kinematics tells you how objects change, and dynamics tells you the forces and the torques that act on objects. So time evolution is really important, and time evolution is described by an equation that is generally called an equation of motion. So you solve an equation of motion and you get the motion, correct? That's what an equation of motion does. It sets up the template on what happens when a force acts on an object, and if you solve that equation, you get the time evolution or the time trajectory of an object. So can you give me an example of the most famous equation of motion in classical physics, in classical mechanics? Yes, please. Oh, right. Okay, that's not an equation. Right. So Newton's law, Newton's equation of motion is kind of the holy grail of classical physics. It's an equation of motion. And what is that equation? F equals ma, or I could write A equals F over m, correct? Now A is the acceleration of an object. It's the double derivative of distance of, so I can also write this as d by t of the velocity, and the velocity is the derivative of position. So I can write this equation as 1 over m into f. So this equation is a differential equation because it involves derivatives. You solve this equation, and what do you get? You get the act of solving this equation yields some variable. What do you get as a result? You get x, or the position. So you solve this equation the act of solving this differential equation yields or produces an x, and that x is a function of time. So this is your equation of motion, whereas this is the solution to the equation of motion. So you must have recourse to some technique to solve this differential equation. So this is a classical equation of motion that describes how objects move, how their velocity is changed, and these objects could be small particles, they could be ants, they could be butterflies, they could be snakes, they could be reptiles, amphibians, they could be human beings, locomotives, they could also be planets, stars, galaxies, and so on. This is the power of Newton. Newton's kind of ambition was to understand the universe, and that's what you've been learning about in your classical physics course. Now we have stepped into the quantum world, so we must have analogous equations in the quantum world that describe how objects change with time. When we talk about quantum objects, what are we interested in looking at? We're interested in looking at quantum states. So we really want to know how quantum states change with time. So we want to devise an equation of motion for quantum physics. The only problem is that neither can you derive Newton's law, this equation. This equation cannot be derived from anything simpler. It's like an axiom. Have you ever seen a derivation of F equals ma? No, you haven't. So it cannot be derived per se. It can be motivated, it can be invoked. Similarly, many equations of motion cannot be derived. So this is an example of an underivable equation. We have a similar equation in quantum physics that talks about quantum states. So the first question I would like to ask you, what kind of equation is this? Is it an algebraic equation, a trigonometric equation, or a differential equation? It's a differential equation. All right. What's the order of this equation? It's second order because of this double derivative. Has everyone dealt with differential equations of some kind, especially in the mechanics course, right? Everyone has done differential equations. Please rectify me if I'm wrong. So this is a second order differential equation. Is it linear? It's linear. It is linear. It's second order, but it's linear because x only appears with the power of 1. You do not have x being multiplied with another variable, and neither it's x squared or x cubed. So it's a linear first order differential equation. But I would like to tell you that really so one might argue that this is a second order differential equation, but when you look deeper into classical physics, this equation of motion is also first order. Let me describe how. In any classical system, so I'm talking about the equation of motion for classical systems. So this is not quantum physics, but it actually kind of is related to quantum physics. I would like to state upfront that the state of a system, we can also talk about states in classical physics. If you have a particle, it also has a state. And you look at the mechanical state of this object, it comprises two parts. It has a position, function of time, and it has a momentum, function of time. So if I look at the position and the momentum as a pair, then these variables define the state of the system. If I knew the position and the momentum, I can tell all that is to be known about the mechanical state of the system. So far, I have not put thermodynamics into the picture, because if I put thermodynamics into the picture, then I have to deal with pressure, volume, and entropy as well, and temperature. But I'm not talking about thermodynamics, I'm talking about simple classical systems, like objects, like myself, like all of you, like everything in this room, and so on. So I need to define a position and a momentum. In fact, the equations of motion for a classical system can also be written as an equation of motion for the state. So this is the classical state of a classical object. Just like we have psi, ket psi as a quantum state, this pair of numbers, this ordered pair of numbers, position and momentum, describe the state of a classical system. And I can come up with a first order differential equation that describes the state evolution, that becomes an equation of motion. The only thing is that there are two such equations, and both of them are simultaneous equations. They work together with one another. So if I were to write down the equation of motion not in terms of the position but in terms of the state, the equations turn out to be the following. The first equation is dh. I'm going to describe what is meant by h. dh over dx is minus p dot. P dot means the derivative with respect to time. That's another way of writing derivatives. This is my first equation. I'm going to describe what h means. The second equation is dh dp, the derivative of h, whatever h is, with respect to momentum is dh by d. This is x dot. In fact, it's better to write these equations. Are you familiar with partial derivatives? No? Some people say no, so I just use this, right? Okay. So these are two equations. They are the equations of motion for a classical system. These equations are called Hamilton's equations. Hamilton's equations. Are they first order or second order? First order. Each one of them is a first order equation. They are the equation of motion for classical systems. So truly and really, even in classical physics, the equations of motion are first order. It's just that there are two of them, because the state has two variables. There's a position variable and a momentum variable. So you need to tell how the position changes with time, and you need to tell how the momentum changes with time. Now what is h? H in classical physics is called the Hamiltonian. In classical physics, this is just another fancy way for the energy. It's a fancy name for the energy. Now let me give you an example of why, just to motivate you that this is indeed an equation of motion. Suppose I'm teaching a little bit of mechanics here. This is my ground here, and I have an object that's falling to the earth. So I drop an object. The object has a certain mass. So the mass of this object is m. Is acceleration due to gravity. The height of this object, let's suppose at any instant of time, let's call it x. It's a function of time. Of course, the object is coming down to the ground, and this object has a certain momentum as well. That momentum is p. It's a function of time. So let's now write the Hamilton's equations for this simple, very simple system and see if it all makes sense. Now for this object that's falling to the earth, what is the energy? What's the energy of this object at any instant? Yes. So what is its potential energy? M G x. Now this x is a function of time plus the kinetic energy. So what's the kinetic energy? Half mv square. Half mv square, which is v square. Okay, let's write v square. Now what we would like to do, I have a term that includes the position. I need a term that includes the momentum. So can I write this in terms of the momentum? So I put square here, divide by m. So this is the square of the momentum. mv is the momentum of this object. So this becomes so this is the energy of the system. So the energy of the system is written in terms of the two state variables x and p, and x and p are treated independently. Just keep that in mind. X is one variable and p is another independent variable. They're treated independently. All right. Now what the first thing that I need to do is I need to write the energy in terms of the state variables. The state variables are x and p. That's what I've been able to do here. Now let's look at the Hamilton's equations and try to derive an equation of motion and see if Newton's equation of motion is recovered. That's what we would like to do. So if you look at, this is my equation number 1, this is my equation number 2. So if I were to find out the derivative of the Hamiltonian with respect to x, what should I get? What's the derivative of h with respect to x? mg. But what should mg be equal to? Minus p dot. So this is my first equation. That's the result of the first equation of motion. mg equals minus p dot. Now in order to write an equation of motion, I need to kind of eliminate momentum from all of this. So but now I have momentum here on the right hand side. Let's say this is equation number 3. Now let's look at equation number 2, the second Hamilton's equations. I need to differentiate h with respect to p, and if I'm able to do that, what is my result? If I differentiate with respect to p, what is my result? P over m. But p over m must equal x dot. This is my equation number 4. Correct? Yes, please.
Isn't momentum a function of position as well?
We are treating them as independent variables. So p, now from this equation I can find a form for p and insert into equation number 3, so I can get rid of the p variable and just have x variable. So what I need to do, I differentiate both sides of equation 4 with respect to time, and I get p dot equals m x dot. Now I insert this into equation 3, and I'm left with mg equals minus p dot, which is mx. Sorry, p. All right, clear? So now this is my, is this an equation of motion? Yes, it is. Yes, please. किधर? ये mg equals minus p dot है. ठहरो. mg equals minus p dot है. यहाँ से इक्वेशन 4 से p equals mx dot आया. फिर मैंने इसको इंटू 3 लिखा, mg equals minus p dot. इसका मैंने दोबारा डेरिवेटिव लेना है, तो माइनस mx डबल डॉट आ जाएगा. So is this an equation of motion? Yes, I can get rid of the m's, and I'm left with x double dot is minus g. Is this an equation of motion? Yes, please. With respect to time. So this means the double derivative of x, or d square x over dt square, equals minus g. This x is a function of time. Is this an equation of motion? Is this a valid equation of motion? Does this make sense from your knowledge of mechanics? Hopefully a very solid knowledge of mechanics. It does make complete sense. So these Hamilton's equations recover and reproduce your conventional Newton's equation of motion. And if I were to solve this equation, how can I solve this equation? What does solving the differential equation mean? I need to find out x. So how can I solve this equation? I integrate both sides. So I integrate once. So I need to do the integration in 2 steps. I integrate once. What do I get? Minus g t plus some constant. All right. Then I can integrate once more. I will get minus g t square over 2 plus k1t plus k2. This is the solution to my equation of motion. And in order to find these variables k1 and k2, I need to know the position and the momentum at some time. Could be initial time, could be any time. So what we've done so far, we've actually motivated that these first order differential equations 1 and 2, called the Hamilton's equations, they accurately describe the motion of a classical object. And what is important to in any problem is to identify the Hamiltonian. And the Hamiltonian is merely the total energy of the system. So if you are able to define the Hamiltonian of a system, you can work out the equation of motion for that system and reproduce and track the trajectory of that object, its position and momentum in time. You can see how the state evolves in time. State evolution means you're looking at the evolution of position and momentum. Now, homework problem, Salman and Dia, I think you should give one homework problem about a kind of spring attached, mass attached to a spring. Write down the Hamilton's equations and find out the equation of motion and so on. Yes, please. In some cases you can, but in many cases you can't. In some cases you can do that, others you cannot. All right. So equation of motion, what do I learn from this? Equation of motion, equation of motion needs one to identify a state. Then you need to have some guiding principle to writing down the equation of motion. Our guiding principle is the Hamilton's formalism, Hamilton's equations. But that needs you to know the energy of the system. So you need to know the energy of the system, you employ Hamilton's equations, get the equation of motion, solve the equation of motion and get the trajectories. Got it? So this is the general scheme of the idea of an equation of motion. All right. Now what I would like to kind of mention is the second point for this lecture is, I hope you all know how to solve a very simple differential equation. So I just want to give you an example of a solution of a differential equation. And I'm sure you've kind of mastered these techniques in prior courses. All right, so let me write in a differential equation, a first order differential equation. My differential equation say is d y of t. Now my y is a function of time. My y is a function of time, and I'm writing a differential equation. So I put some number here a plus b y of t equals 0. This is my differential equation. Forget about physics, let's look at the maths. So this is my mathematical first order differential equation. It's linear, y doesn't have squares or cubes, it's not being multiplied with anything else, with any other variable, that is. So how do I solve this?
You take b to the other side.
So there are different techniques to solve this. So any ideas? Yes, please.
Replace y with vx.
Y with
Vx.
Vx. There's no x, right? You don't need to introduce yet another variable. Yes, please.
You have the differential added to the regular function, which kind of looks like the product rule. So maybe we can try to induce that.
Right, we want to use some kind of product rule. Yes, please.
We separate a and b to one side and
Then what? That's a triviality, but then what? So what should the solution of this equation look like? Straight line, sloping line, straight line. Let's see. Any takers to this question? Have you taken further maths or something? FSC mathematics is not? No, all right. Yes, please. No, but there's one variable. There's no need to separate. There's one variable y. You don't need to separate.
sir, we take by b y t to the other side and a over b.
Doesn't matter. So let me see how this equation can be solved. I need to follow this because this is going to matter. So I just look at this y plus b over a, y equals 0. This is just a trivial operation. Now what I would like to do, the kind of recipe for this is, there's this function y, there's the derivative here, the first order derivative, and just the raw function y, no derivative here. This y comes with a coefficient b over a, which is a number. Now what I would like to do, I like to define an exponent factor, an exponentiating factor. I define e and in its power I write down the integral with, now what's my parameter here? My parameter here is time. My variable is y, but my parameter is time. The variable varies with the parameter. So I'm looking at the time dynamics. So I differentiate integrate with respect to time, and what I put inside the integral is this coefficient b over a. So I take e exponent raised, and in the power I put an integral sign, and what do I integrate with respect to the parameter which is time, and what do I integrate? What is my integrand? It's the coefficient of y, b over a, which is a constant. So what would this give me? E raised to power b over a is just a constant, and what's the integral of integral dt? Integral of 1 t, not dt, it's 1, right? It's t. Forget about plus c for a minute. All right. So now what I'm going to do is, this is my, I call this an integrating factor. I multiply this equation with the integrating factor. E raised to power bt over a dy by dt plus b over a e raised to power bt over a y equals 0. So I multiplied both sides with the integrating factor. Now this comes to the point that my friend at the back really kind of highlighted, is that this entire expression is the derivative of something. I can invoke the product rule. So this entire function is really the derivative of e bta multiplied by y, isn't it? So just use the product rule here. So if I work my way backwards, a derivative of a product of two functions is the first function multiplied with the derivative of the second function plus the second function multiplied with the derivative of the first function. This is what this top line represents, and I am able to do that because of the exponentiating factor, because of the integrating factor. Now I have a derivative of something equaling 0. What is that something? It's a constant. So this means that my something, which is in the big brackets, is a constant, some k. All right. Now this means that what I could do is, I could take this exponentiating factor, which can never be 0. The exponent of something can never be 0. So I can take this to the other side of the equation, and I'm left with k e minus bt over a. Correct? Is this a solution? This is indeed a solution to the original differential equation. And what is this value of k equal to? How can I determine the constant k? What's the initial condition? If I put time equals 0, then k is just the value of y at time equals 0, because this turns out to be 1 at that point. So this k is really y at time 0. Hence the solution to this original differential equation, the solution to this equation is y at time 0 into e raised power minus b over a into t. Got it? There's a question here. Yes, please.
Can you explain second term का भी है?
इधर
Yes. जो second term है b over a into e power b.
इसको डिफरेंशिएट करके देखो ना, जब आप एक्सपोनेंट को डिफरेंशिएट करते हैं तो b ओवर a वैसे आ जाता है बाहर, ठीक है? यस प्लीज.
आपने e इंटीग्रेंड dt over ba किस तरह से बनाया है?
I've just take e integral with respect to time, everything is happening with respect to time, and what I put inside the integral, which is the integrand, is just this coefficient. Whatever comes with y, the non-derivative term, I put it there. Yes, please. आने दो, मुझे A level नहीं आता. मुझे नहीं याद वो क्या है. तो there could be multiple techniques. You can do that. I'm not sure what you're referring to, but that's also a very legitimate approach. Yes, please. Anyone else? So this is our solution to a differential equation. Now cherry points for anyone who could kind of plot y versus time. Could you kind of flash how this graph is going to look like? Can you first answer my question? कैसे होगा? It's going to be an exponential decay. This point is y equals 0, and kind of the decay is determined by a over b. Higher a over b, faster will be the decay. Slower a over b, lower a over b, slower will be the decay. So a over b is like a time constant. Yes, please. B over a is the rate of decay, and a over b is the time constant. All right, so this is how you solve a differential equation of first order, and this carries over to quantum physics as well. Now, excuse me, it's very important. If you want to solve a differential equation and you get a solution of this kind, any differential equation that is of this kind, any differential equation, provided a and b are constants. Excuse me, interrupt ना किया करो please अपनी आवाज़ों से. If a or b are constants, they don't change with time, and you have an equation of this kind, all such equations will render a solution of this kind, which is of this general form. The variable that you're interested in varies with time, and how does it vary? You look at what the variable was at time equals 0. That's this point over here, and then you see how it changes with time, and it exponentially decays. This is what this equation of motion, or this differential equation, yields. Now let's jump over straight away to the quantum equation of motion. And the quantum equation of motion is called, any guesses? The Schrodinger equation. And there are two kinds of Schrodinger equations, or two versions of the Schrodinger equation. The version, first of all, we're going to talk about the time dependent Schrodinger equation. The time dependent. Sometimes I can write this as TDSE. Now, generally, when you take a course in quantum physics, probably in the other modern physics class too, generally you start off with the time independent Schrodinger equation. But now I've taken a kind of different route. I'm explaining the more difficult part first, but actually this is, as it turns out, this is the easier part. Now let me write down the time dependent Schrodinger equation. Since I cannot derive it, let me just write it down. The time independent Schrodinger equation. Now what's my quantum state? What is my quantum state? How do I represent quantum states? Kets. Kets are my quantum state. In the classical example, position momentum were my state. Now my state is quantum state. So I need to have some first order derivative of the quantum state. So, and I also need to have some kind of energy in there, some kind of Hamiltonian in there, just as I had in the Hamilton's equations. The meaning of Hamiltonian is the same, exactly the same. It's energy, but it's kind of a more complicated mathematical object. So the time dependent Schrodinger equation is iota h bar, the time derivative, time dependent psi, and since my state is a function of time, I explicitly write the time dependence ket psi, but now psi is a function of time. When I transform quantum states, I doing transformation, each one of them is happening in time. So I kind of hid away the time dependence in the previous 12 lectures, but there is some hidden time dependence in all quantum states. Now I'm exposing this time dependence in front of you. So this is the left hand side of the time dependent Schrodinger equation, and this equals the Hamiltonian acting on the quantum state, and the Hamiltonian is now strange object, so I put a hat on top of it showing that it's an operator. So just give you 1 second to look at this. Just look at this. No question, just look at it. All right. Let's look at the main features of this equation first. Is it first order? Yes. Is it linear? Linear because it doesn't have products of quantum states and so on. It's linear. Is there anything strange that you find in this equation? This has a complex character to it. This has a complex number in here. So it has an iota. And this object here is not a number. H is, although it's refers to the energy, but it's not a number. It's an operator. It's a matrix. This operator is now a matrix. That's the only difference that you have from classical physics. In classical physics, you didn't have any matrices. Now you are dealing with a matrix, an operator. This operator acts on this quantum state. I'm going to see what the meaning of this operator is, but H is an operator. Operator. H is called the Hamiltonian. The Hamiltonian operator. The other thing that you find kind of unusual, probably the first time you're seeing this, is that now we're looking at the derivative of not a function but a ket. And a ket lives in a Hilbert space in a complex vector space. This is a vector. You're looking at the derivative of a vector, of a ket, of a quantum state. So it's a derivative of a vector. So it's not the derivative of a function. You can make it into a function, but it's really at the outset it's a derivative of a vector. So you have a derivative of a ket. Now this is actually an aesthetically powerful symbolism that's in front of your blackboard at the moment. It's astounding in its beauty, astounding in its power. It can explain how lasers work, how superconductors work, Bose-Einstein condensates, how molecules form from atoms, what is chemical bonding, what is quantum mechanical tunneling, why does ammonia molecule occur in one shape then goes to another. It explains so many different things in nature. This simple kind of spattering of symbols in front of you. Now let's solve this equation, but I don't want to go to the drill of solving this equation. Can you compare this equation with the equation that we have over here and use this solution and write down the corresponding solution to this equation? I give you 2 or 3 minutes for this, please. Can you solve this equation? You don't need to do the derivation again, just look at the result that we have over here and map it to this problem. Suppose H is some object, forget it's a matrix, it's some object, just treat it as it is. So on the left hand side, the solution to this time dependent Schrodinger equation is psi at time t. This is a ket. This equals, now I need to know the quantum state at time t equals 0. This is my quantum state at time t equals 0, but now this is a ket. So what I need to do, I need to have an operator that acts on this ket. So I need to put the operator on the left of this ket. That's what we've been doing so far in this course. If you have an operator, it acts on the ket from the left. The operator is the predator and the ket is the prey. So it just opens up its claws and feeds up and devours the state. So this is minus. Now if I were to take iota to the other side, this would become minus iota. 1 over iota is minus iota. This goes into the denominator. So I'm left with iota Hamiltonian h t over h bar. All right. Yes, please. We can't do that because I'll explain. Any more questions? So I can write this in 2 fashions. I can put 1 over iota with a positive sign or minus iota. The same thing. 1 over iota is minus iota. 1 over iota is minus iota. Alright, remember this. So this is the solution to the time dependent Schrodinger equation. Now we're going to have a break. Just give me 2 minutes, please. This is an operator. H is an operator. The Hamiltonian is an operator. So what I'm doing now is a very strange thing from the perspectives of algebra. Excuse me. I'm putting an operator as an exponent in the power of e. So now I have an operator in the exponent's place, in the power place. I need to figure out how to compute such a thing. The Hamiltonian, the matrix is now going into a power. How do I compute this? I'll show you ways how to do that. But overall, this entire thing is an operator. All of it is an operator. This operator must act on a ket. So it's impossible to have a scenario like this, ket psi being multiplied by any operator, because this is a matrix, this is a column vector. They will not even be compatible for multiplication. So an operator always acts on a ket from the left. The operator has to be written to the left of a ket. Now what we're going to do after the break is we're going to understand and start interpreting the solution to this time dependent Schrodinger equation. Let's meet after 10 minutes. Now what I would like to do now is I would like to kind of unfold and unpack this equation. Let's look at a specific example. What I would like to look at now is a proton inside a magnetic field. You're disturbing the entire class. So I'm going to describe a technology. In this part of the course, we're going to be very applied, very application oriented. Now we have all the arsenal with us. We have all the tools, all the techniques with us. Like to talk more about technology and applications. So the technique that I'm going to describe now with the formalism that we've developed and with the time dependent Schrodinger equation that we've introduced, I'm going to introduce to you this phenomenon and technique of nuclear magnetic resonance, NMR. And associated with it is MRI, magnetic resonance imaging. Now in NMR, it's a quantum mechanical phenomenon. It's a kind of quantum computing phenomenon, and all the kind of bits and pieces that we put together, they become ingredients to understand NMR. In NMR are qubits. We have qubits, and in NMR the qubits are neither photons, neither polarization of photons, neither are the electrons, they're actually protons. And a proton is a hydrogen nucleus. There's lots of water in our body. 70 to 80% of our body weight is due to water. Water is hydrogen oxide, dihydrogen oxide. 2 protons in a water molecule. It's a rich source of protons. Our body is an extremely rich source of protons. Now each proton, like an electron, acts like a spin, a tiny magnetic dipole, and they respond to magnetic fields. Now if you recall from our earlier lectures, now this is just a cartoonic representation of a proton. A proton has a spin. It's not spinning, but it has a quantum mechanical property called spin. Associated with this spin, let's call the spin S. Associated with the spin, there's a magnetic moment. We all know that. The magnetic moment associated with the spin equals some constant g, charge 2 times the mass of the particle and then S. We've already derived this relationship. Associated with an angular momentum, there is a magnetic moment. And this was our kind of derivation. Yes, please. अभी नहीं आएगा. And since angular momentum, now we're not talking about the orbital motion, we're talking about the spin angular momentum of a proton. It's a vector, so the magnetic moment is also a vector. And if you were to talk about the proton, This E becomes the charge on a proton, correct? This mass becomes the mass of a proton, and G is a factor that is associated with protons. G for protons is roughly equal to 5.67. So this value comes from nuclear physics. It can be derived as well. So anyway, all of this gives a constant of proportionality. Now if we were to place this proton inside a magnetic field B, so we place this proton inside a magnetic field, what's going to happen to the spin? It will try to align with the magnetic field. Why does it align with the magnetic field? Because that lowers the energy. We know what happens when a tiny dipole or a spin is inside a magnetic field. There is an energy associated with it. That energy E is, from classical physics, we know it's given by minus mu dotted with B. So for a proton spin, this energy inside a magnetic field is minus G E over 2 MP S dotted with B. Correct? So far so good. Dot product. Now what direction is the magnetic field pointing in? Suppose this is my Z direction. My magnetic field is pointing in the Z direction. So this angular momentum is also a vector. So what will this dot product equal to? It's going to be just the Z component of S multiplied with B, because it's a dot product. So this turns out to be minus G E over 2 MP B S Z, the Z component of the spin angular momentum. All right. I just give you two minutes to kind of go through this, your previous notes if you wish to, and go through this derivation. The energy is, this is the formula for the energy of a dipole inside a magnetic field, mu dot B, with a minus sign. Look at my previous lecture notes. If mu is parallel with B, the energy is minimized, it's lowered, so that's why we have a minus sign here. The magnetic moment wants to align with the field, that's why it's a dot product. Because when it's a dot product, alignment means an angle of 0 that maximizes this object. So this is the formula for the energy, and what I've done simply is I've taken this value of the magnetic moment, put it here. I take the dot product of S with B. B is inside the Z direction, so I just need to focus on the Z component of the angular momentum. Very simple. Now this is my energy. This constant here for a proton is given a special symbol gamma. Gamma. This gamma is called the magneto-gyric ratio. In all books it was called the gyromagnetic ratio. Same thing. It's the magneto-gyric ratio. Magneto means it connects magnetism with angular motion, gyroscopy. So it's called the magneto-gyric ratio. All right. So my energy really is minus gamma B S Z. All right. No quantum physics so far. Only that the value of G is derived from some quantum physics, and the proton has a spin because of quantum physics. But the equations so far are totally classical. Now this object here, gamma B, if you were to find the dimensions of this object, they would turn out to be per unit time. The dimensions are 1 over time. 1 over time per second are the units for this object, per second. So you can work this out. G doesn't have any dimensions. Q, you know, its charge. Mass, you already know. So work out, you'll find out, and you multiply this with Tesla. All of this has units. This entire thing will have units of per time. Homework problems. Salman, is he here? No one here, okay. So this has units of time of, 1 over time. It's like a frequency. 1 over time is a frequency. So you have to work this out. So I can't tell everything in the class. Work this out. So I call this minus gamma B, I give it a symbol, and I call this omega, angular frequency, radians per second, SZ. So this is my energy. All right. Now if I were to kind of enter the world of quantum physics, I want to convert this equation into an operator equation, because in quantum physics my Hamiltonian is an operator. So now, but this is a classic, this is a number. The units for this will be joules. This energy has units of joules. All right. Now one effect I would like to mention here is, I'm going really slow here so that everything is clear. These are new concepts, so you'll be a little bit surprised, but I'm showing you I'm going really slow. So now one idea I would like to present at this point, point number 5, is the Zeeman effect. Now quantum physics tells us that the z component of the angular momentum of the spin of a proton or an electron is quantized. Remember the quantum numbers for the electron inside the hydrogen atom? Remember the fourth quantum number, ms? What values could it take? Plus half and minus half. Because it was spin, the electron is a spin half particle. Therefore, this Sz can take up the values h bar by 2 or minus h bar by 2. So this Sz is really equal to ms h bar, where ms can take up values of plus half and minus half. This is just the Stern-Gerlach experiment. Remember the Stern-Gerlach experiment? The two beams of electrons that just carried the spin with them, they bifurcated into two beams, one corresponding to an angular momentum spin of h bar over 2, the other minus h bar over 2. One corresponding to a quantum number plus half, the other corresponding to a quantum number minus half. It's exactly the same quantum numbers here. So this Sz here is quantized. Spin is quantized inside a magnetic field. And so this leads to two kinds of energies, by the way. One of these energies is h bar omega over 2. So I just put Sz equals h bar over 2. This is one energy. The other possible energy is minus h bar over 2. So a proton inside a magnetic field can have two kinds of energies. Which one of these is lower? One of them is going to be lower. Depends upon the sign of gamma. If gamma is positive, omega is negative, this is the lower energy. The other would be the positive energy. In any case, there are two energy levels. And if I were to make an energy level diagram, there are two energy levels corresponding to the two configurations of the spin. If the spin points parallel to the magnetic field, the energy will be lower. It will be this case, because omega now is negative, but you can forget that for a minute. One of these energies is minus h bar magnitude of omega over 2. The other energy is plus h bar omega over 2. One corresponds to the spin pointing up parallel to the field. The other corresponds to the spin pointing opposite to the field. One can be called ket 0, one state. The other state of the spin can be called ket 1. One is parallel to z, the other is anti-parallel to z. So this is the Zeeman effect. The Zeeman effect is that when you place a spin inside a magnetic field, the energy levels are split. One becomes lower in energy, the other becomes higher in energy. How much is this gap? How much is the gap? It's h bar omega. This is the gap between these levels. These levels are called the Zeeman levels. And if you increase the magnetic field in which you place the spins, what's going to happen to this gap? Will it go up, down, stay constant? Sorry? It will increase?
Yeah, the gap.
The gap is going to increase. Why is it going to increase? Because omega is proportional to the magnetic field. Higher the magnetic field, the gap is going to open up, open up, open up. So if I were to make a diagram, this is my magnetic field and this is my gap. Let's call this energy gap delta E. So what if my field is 0? What's the gap? 0. If my field is 0, the gap is 0. So the two energy states are indistinguishable. The two quantum states cannot be discerned from one another. They cannot be told apart because the two gaps have the same energy. These are called degenerate levels. Now you increase the magnetic field, the gap slightly opens up, it fans up, keeps on increasing. So increase the magnetic field, the gap goes up. All right, and in the other direction the gap also goes up. So this is the opening up of the magnetic field gap. Now this is the Zeeman effect. But keep in mind that this gap is h bar omega, and you're familiar with energies of this kind. What's the energy of a photon? hf or h bar omega. So if a spin comes from the top state to the lower state, which means its spin was anti-parallel, becomes parallel, it emits a certain amount of energy in the form of light, in the form of photons, and that photonic energy is h bar omega. Now what we're going to do is we're going to continue with our NMR experiment. The first thing we would like to do is we would write the Hamiltonian. All right. Before I'm able to write the Hamiltonian, is everything clear so far? Quick question? Yes, please?
Why are they called degenerate?
Degenerate. That's just a name for them. They kind of have the same, any two energy levels that have the same energy. In physics, they're called degenerate. Yes, please?
What is MS H bar?
MS H bar is SZ. And MS can take two values, plus half and minus half.
So MS is a constant.
MS is a quantum number. Yes, please?
सर जब स्पिन अलाइन होगा तब फोटोन रिलीज होगा
नहीं, जब ट्रांजिशन होगा between states. Energy needs to be conserved in all processes. Yes. Well, the lower energy one will be parallel. Okay. Now you have two energies. You need to decide which one of them is lower. If omega is positive, this will be lower. If omega is negative, this will be lower. Yes, please.
But in order for the transition to happen, it must have to align or disalign, right?
It must change its spin. Now, before I describe the Hamiltonian for the NMR problem, we know the energies, right? We know this energy for a proton spin inside a magnetic field. From this energy value, we need to infer what the Hamiltonian matrix looks like, because the Hamiltonian matrix does correspond to energy. The Hamiltonian is the energy. The only thing in quantum physics is that this Hamiltonian is now a matrix. So that slightly complicates something, and that's the only difference you will find with classical physics. Now, in order to write the Hamiltonian, first of all, I would like to introduce three matrices, three kinds of matrices to you. And you've already seen them. One of them is the X matrix. This X matrix looks like this. Is this a unitary matrix? Yes, all of these are unitary matrices. The other matrix is Y. 0, minus iota, iota, 0. So these are just definitions of these matrices. The third matrix you need to know is the Z matrix. 1, 0, 0, minus 1. All of them are unitary matrices. All three of them. They're unitary. Their complex conjugate, Hermitian conjugate equals the inverse. This is also a phase gate with phi equals pi. These three matrices have a special status in quantum physics. And they're so important that they've been given a special name by their inventor, and these are called Pauli operators or Pauli matrices. Pauli. Now they have an interesting property. A Wolfgang Pauli, yeah. So if you take the square of any of these matrices, it turns out to be the identity. So I'm writing a hat on top of 1, indicating it's an identity matrix. So you take this, any of these matrices and square them, it becomes a matrix. So these are the three Pauli operators or Pauli matrices that you'll frequently encounter in the next 2 or 3 lectures. All right. Now, with the help of this definition, I am now able to write the Hamiltonian corresponding to this energy. So what I need to do, and you need to take me on faith on this. If I know the energy, the classical energy, what I would do, I want to write down the Hamiltonian matrix. My Hamiltonian matrix H is going to be equal to omega now SZ can take up these values h bar over 2 and a minus h bar over 2. So I can have a value h bar over 2 with a plus sign or a minus sign. Now in order to incorporate that plus sign or a minus sign, I need to put in a matrix. Which matrix do I choose from these options? If my magnetic field points in the z direction, I choose the z matrix. If my magnetic field points in the x direction, I choose the x matrix. If it points in the y direction, I choose the y Pauli matrix. So this is how I write down the Hamiltonian for a spin half particle, aka a proton, inside a magnetic field that points along the z direction. Yes, please.
So for that same proton, the Schrodinger time dependent equation, the Hamiltonian
Is this.
is this.
Now can you write this in matrix form? What will it look like in matrix form? Right, so in matrix form this will be h bar omega over 2 0 0 so this is the Hamiltonian for a proton inside a magnetic field pointing along the z direction. Got it? Very simple, very simple. So now we have the Hamiltonian for this problem. We can kind of see how the state evolves with time because we already know what the time dependent Schrodinger equation solution look like. One aside, one digression. How many of you taking the linear algebra course? A vast majority. So do you know what the eigenvalue of a matrix is? Yes. Have you studied it in the course so far? Yes or no? No. Don't be afraid of your peers. I mean, पढ़ लिया? Right. So just that's why this is a digression. The eigenvalues of the Hamiltonian, excuse me, the eigenvalues of the Hamiltonian are the energies. If you take this Hamiltonian, it has two eigenvalues, h bar over 2 and minus h bar over 2. Those eigenvalues are the energies. So you can even write this in golden words. One day you will study eigenvalues. So then you can recall the eigenvalues of the Hamiltonian operator are the energy values. So if you were to measure the energy of this system, these are your outcomes. If you measure the polarization, there are certain outcomes. You prepare certain states. In this case, you are going to prepare these energy states. These will be the values for the energies that you measure. So the eigenvalues of the Hamiltonian are the energy values. All right. Now the question is, the question is, now I have the Hamiltonian with me. I need to find this object. I need to find this operator because knowing the Hamiltonian is not sufficient. I need to put the Hamiltonian inside the power of an exponent. Now how do I do that? Okay, slow. Okay, let's see how we do that. So first of all, let's look at this operator here. So let's call this operator U, because you learn later in a course on quantum physics it's a unitary operator, but let's call it U. U is E minus iota h t over h bar. So now for our problem at hand, which is a spin inside a z pointing magnetic field, we already know what the Hamiltonian looks like. So this is E raised to minus iota h bar. My Hamiltonian is now given by this thing, h bar omega over 2 z into t. All of this is inside the exponent. This entire thing is inside the exponent. So don't be befooled by anything else. This is in the exponent. Some books would write this as exponent of minus iota h bar omega over 2 z t. So by the way, this h bar goes away, and this becomes exponent minus iota omega t over 2 z. So this is the operator. This operator acts on the initial quantum state to give me the quantum state at some later time. So now I have solved the time dependent Schrodinger equation. The only thing is that I need to make physical sense out of it. All right. All right. वैसे इससे ज़्यादा खूबसूरत चीज़ देखी आपने कभी? Now the question is, the question is, now I have the Hamiltonian with me. I need to find this object. I need to find this operator because knowing the Hamiltonian is not sufficient. I need to put the Hamiltonian inside the power of an exponent. Now how do I do that? Okay, slow. Okay, let's see how we do that. So first of all, let's look at this operator here. So let's call this operator U, because you learn later in a course on quantum physics it's a unitary operator, but let's call it U. U is E minus iota h t over h bar. So now for our problem at hand, which is a spin inside a z pointing magnetic field, we already know what the Hamiltonian looks like. So this is E raised to minus iota h bar. My Hamiltonian is now given by this thing, h bar omega over 2 z into t. All of this is inside the exponent. This entire thing is inside the exponent. So don't be befooled by anything else. This is in the exponent. Some books would write this as exponent of minus iota h bar omega over 2 z t. So by the way, this h bar goes away. And this becomes exponent minus iota omega t over 2 z. That state going to change with time. So in order to do that, I need to kind of have another kind of form of this unitary operator, because I haven't yet learned how to exponentiate operators, how to put matrices in exponents. I haven't learned that so far. But what I have learned is something similar. I know two things. One, I do know that if I were to take any of these operators and I square them, I will get identity. And I also have something which is called the Maclaurin series. Now, you don't be never be frightened by these kind of tricky names, especially names of people. So the Maclaurin series is a kind of nice way of finding out different functions. So let me write down the Maclaurin series for you. You don't need to remember it, but repetitive use makes you remember things. So we use it all the time, so everyone knows this, everyone remembers this. So this series goes as follows: e raised to iota theta gives us one. Okay, let me just kind of first put some number here, x. E raised to some x, some number, some scalar is 1 plus x. You generally want x to be smaller than 1, by the way, it's a small number, plus, but it doesn't matter, the series still holds, x square over 2 factorial plus x cube over 3 factorial plus x4 all right. So this is called the Maclaurin series. Maclaurin series. X is a number, I can exponentiate x. किसी को अप्रोच नहीं करेगा, e raised to x को अप्रोच करेगा. All right, you need to understand this. So now what I'm going to do, instead of x, I'm going to put a matrix in the exponent. So e raised to a matrix, some matrix A. Now A is a matrix, and just in one step I'm going to put some number with it, a scalar theta, some number theta. It's a real scalar theta, and I'm going to put an iota here as well. Also in homework number 1, can you identify what the series means? It's cosine theta. It's cosine theta. This is sine theta. All right. Therefore, e raised per I theta a equals cosine theta identity plus I sine theta a. And if there is a minus sign here, a minus sign will appear here. So this is true if a square is identity. Very nice. Because now what this does, this is something you can easily find because there is no exponent here. This is just cosine theta multiplied with identity plus minus iota sine theta multiplied with the matrix itself. So now you've converted the problem of exponentiation of a matrix into something really simple. Now can we, with this knowledge, find out what this state is going to look like? Now I leave this as your kind of problem and we'll continue with this on Tuesday, inshallah.